Right, so hydrostatics, the basic principle to begin with in hydrostatics is so the basic thing to start in hydrostatics with is the concept of pressure gradient. So as you know, when you have a stationary tank, there is only vertical pressure gradient. There is a fluid of density rho, which is in a stationary tank which is not having any acceleration or velocity, and we take our standard y-axis to be vertical and x-axis to be horizontal. So then we know that the horizontal pressure gradient is 0, whereas the vertical pressure gradient is minus rho g, which means that if you consider any 2 points which are at a vertical height difference of h, the pressure difference becomes rho gh. In this case, E is above P, so it will be at a lower pressure. Or we can say that pressure at a lower point will be at the pressure at the highest point plus rho gh. Okay. So the entire first section, hydrostatics, is mainly based on applications of this equation, that vertical pressure gradient exists directly proportional to gravity and height difference in the case of a stationary tank. So let us see some examples based on this. So now we have this kind of a situation, suppose. This is a fluid of density, let us say 4 gram per cc. Inside this we have this point E, this point B, this point on the surface C. So this is a depth of 5 meters, and this is also a depth of 6 meters. Given atmospheric pressure, approximately 10 raised power 5 pascals or 100 kilopascals. Find the pressure at E and the pressure at B. Just work this out quickly. Just send me the answer to these 2 parts in text. Okay, so far Manishka has sent the correct answer. So you can see the C is a point which is at the open surface. Okay. So pressure at C will be equal to atmospheric pressure, which is 100 kilopascals or 10 raised power 5 pascals. Now you can see that the height difference between C and E you can see that if you take the vertical coordinate like this, y-axis upwards, you can see that y of C minus y of E is plus 5 meters. Okay, so that means pressure at C minus pressure at A should be minus of rho g into 5 meters. In other words, pressure at A should be equal to pressure at C plus rho g into 5 meters. And similarly, pressure at B should be equal to pressure at C plus rho g into 11 meters because the height difference is 11 meters. Okay. So from this, you'll be able to calculate the pressure differences. So just work this out numerically. So now just use the equations to work out numerically the pressure difference between these. So anybody else got the answer? Yeah, so what about the others? Yes, Manishka, you made a mistake in the unit conversion. Now it is clear, I hope. Anybody else got the answer? So far only Manishka has given the answer. What about the others? Okay, so let's get to the detailed calculation. Should be fairly standard for everyone. So this one it is 11 meters into this. Okay. So pressure at E finally will become 10 raised power 5 plus, now see, 1 gram per cc is 10 raised power 3 kg per meter, and we take acceleration due to gravity as 10. Okay. So this will become 10 raised power 3 into 10 into 5. So this will become 10 raised power 5 plus 5 into 10 raised power 4. So it becomes 1.5 into 10 raised power 5 pascals. That should be the pressure at the point. Right, so the conversion factor is important over here. You remember that 1 pascal is equal to 1 Newton per meter square, which is 1 kilogram meter per second square per meter square. So it is equal to 1 kg per meter cube into 1 meter per second square into 1 meter, like that. In terms of rho gh, 1 pascal is equal to this much. And also you should remember this conversion factor, because 1 gram per cc is 10 raised power minus 3 kg per 10 raised power minus 6 meter cube. So 1 cc is 1 centimeter cube. So that is 10 raised power minus 2 ka whole cube. That's 10 raised power minus 6 meter. So hence this conversion factor. Okay, so rho g h becomes this. Okay. Similarly, pressure at the point B will become pressure at C, which is 10 raised power 5 plus rho into g into h, which is 11 meters. So you can see it as 10 raised power 5 plus 1.1 into 10 raised power 5. So this has a pressure of 2.1 into 10 raised power 5 pascals. So typically we also call the P naught, which is approximately 10 raised power 5 pascals, as 1 atmosphere or 1 bar or even 1 torch sometimes. So the pressure at the point E is becoming 1.5 atmospheres and the pressure at the point B is becoming 2.1 atmospheres. Alright, so let's move on to another question now. The next example is like this. We have this kind of a tube. Now inside this tube, initially what we've done is there is water filled. This is water which has a standard density of 1 gram per cc, and it is filled to a height of h, let us say 20 centimeters. Now next what we are doing here is we are going to pour some kerosene from one side. This is kerosene oil which has a density rho prime of, let us say, 0.8 gram per cc. So when we pour the kerosene, what happens is on one side the water level goes down and on the other side the water level goes up. So we want to find H1 and H2 when kerosene is poured like this. So this is a complete question. We will try this out. Oh, sorry. In the question is given the value of D is given. D is 10 centimeters. The height of the kerosene layer D, that is 10 centimeters. And also assume that the tube is having uniform cross-sectional area. Anybody got the answer, people? So see, I'll give you the hint. The concept we use here is that this point, suppose, is A and this point is B. Now the pressure at the point A must be equal to the pressure at the point B. That's how the liquid will be in equilibrium. Okay. 2 points at the same horizontal level will always be at the same pressure. So, for example, here also that's happening. Pressure at the point D is equal to pressure at the point B. That's why the heights are the same. Okay. But here what is happening? Pressure at the point A is equal to atmospheric pressure plus this layer of kerosene, because here the pressure is atmospheric pressure, then kerosene है, तो इतना height difference की वजह से कितना pressure होगा? It will be density of kerosene into G into that height, which is B. Okay. Plus now here to here there is water, so rho G H1, that is the pressure at the point B. Now that should become equal to pressure at the point B. So pressure at the point B will be just how much? It will be atmospheric pressure plus rho G H2. So you have this relation that density of kerosene into G into T plus density of water into G into H1 should be equal to density of water into G into H2. Or you can just convert this equation to rho prime into T is equal to rho into H2 minus H1. And rho prime is 0.8 gram per cc. So since you are having a ratio of the densities, you can just keep it in gram per cc only. So you have, sorry, H2 minus H1. So H2 minus H1 is 0.8 times D. That's your first equation. Okay. Now another equation has to be generated because we have two variables H1 and H2. So try to think how we'll get the other equation. Okay, so where will the second equation come from? Second equation hint is that volume of water is same. Between the first picture and the second picture, you're not adding or removing any water. So volume of water should remain constant. So now try that out to find out the second equation and solve it. Manishka got the answer? Anybody? Okay, so conserve the volume of water. So what is happening is, in the first case, if the height of water on either side was h, and let's say this length was L, so volume of water was 2h plus L into some area of cross section. In the second case, instead of 2h, you have h1 plus h2 into area. So this equation becomes that 2h is equal to h1 plus h2. L cancels on both sides. So that becomes your second equation. So this height plus this length should be equal to h1 plus this length plus h2. Okay, so that means h1 plus h2 should remain equal to this height plus this height, twice of this. So that's what this equation is. h1 plus h2 is equal to 2h. Now you have the two equations and the two variables. Okay? So you have h1 plus h2 is equal to 2h, which was 40 centimeters from above. H was 20. And you have h2 minus h1 is equal to 0.8 into d, which will work out to be 8 centimeters. So just add these two equations. So you get 2h2 as 48, which means h2 works out to be 24 centimeters, which means h1 will work out to be 16 centimeters. So because of the presence of kerosene, what will happen? The water level will go down on one side by 4 centimeters, go up on the other side. Okay. So this is what will happen. So when you're putting in the kerosene here, what is happening is this is going down by 4 centimeters and this is going up by 4 centimeters. And that's how the kerosene layer here, which is formed, is 10 centimeters. So that is the final solution to the problem. Okay, so this is typical JEE mains type of question. So hope you understood this, people. Okay, now just going back to the previous question one moment. I don't know if you people noticed because nobody told me, but I've taken the density as 4 gram per cc, whereas in the calculation, I've used 1 gram per cc. See, I've used 1 gram per cc. Okay. So just make a correction in the question since I've already done it by this. So this is not 4 gram per cc, make it 1 gram per cc. The calculation is done as per 1 gram per cc. 4 grams will give you a different answer, 4 grams per cc. Okay, let's come to the next section now. So the next section is to do with horizontal pressure gradient. In an accelerated tank. This is more specific to your JEE advanced type of questions. So suppose we have a tank which is actually moving with some kind of an acceleration. As a uniform horizontal acceleration. course, acceleration due to gravity exists. So inside the tank, if there is some fluid, you will see that the fluid surface takes this kind of a shape, becomes inclined. Such that theta becomes tan inverse of E by G. And if your system of axes are like this, there is now a horizontal gradient of pressure and along with a vertical gradient. Okay, so this happens why? Because if you consider a fluid element, if you consider a volume of fluid of mass dm, now it is at rest in the non-inertial frame, which is accelerating like this. So on this there is weight, but there is also pseudo force. So this pseudo force along negative x-axis creates the pressure gradient minus rho e, whereas the gravitational force creates the vertical pressure gradient minus rho e. So that is why in this kind of situation we have horizontal and vertical pressure gradient, and by dividing these two you can see del y by del x becomes E by G. So we have this. Okay. So hope you are familiar with this concept. If not, just make a note of this formula. Okay, so based on this, let's work out a quick example. So what we are observing is this is moving with some uniform horizontal acceleration. And G in our problem is 10 meters per second square. Now what we are observing is while the tank is accelerating, this is like this, where so a rectangular tank accelerates horizontally, acceleration P, such that the water in the tank is as above, where L is equal to 10 meters. H1 is equal to 6 meters. H2 is equal to 4 meters. So find the horizontal acceleration A. Given G is 10 meters per second square. And if the tank now comes to rest, what will be the level of water at equilibrium? So just try out this question now, people. Okay, anybody got the answer yet? No. Yes, Manishka, the answer is correct. Anybody else got the answer? Okay. So you can understand here that in this diagram, you try to calculate tan theta or the inclination to work out this angle theta. Okay. So use the formula tan theta equal to E by G. Now tan theta you can see is H1 minus H2 by L. That is equal to E by G. So if you use these values here, your E by G will come out to be 0.2. So acceleration will come out to be 2 meters per second. So that is the first part's answer. Now also work out the second part's answer. Yeah, Manisha. Second part's answer is for when the tank is stopped from acceleration, then what the uniform level will become. For that, you have to just do volume conservation. So when the tank comes to rest, the level of water should become uniform like this. Now this is like this. Then volume conservation tell us that H into L should become H1 plus H2 by 2 into L. Because this area should be equal to this area. So that area into depth will give you volume conservation. This should become the common method. So this is the second part. Alright, so this is about accelerated tanks. Okay, next we look at Archimedes' principle and the concept of buoyancy. So as you know, the statement of Archimedes principle is that buoyant force or upthrust is equal to the weight of fluid displaced, or that equals to the density of fluid multiplied by the volume of the submerged part multiplied by G. So that kind of situation. So let's start with simple example here. So let's assume we have a situation like this. This is thread which is used to suspend solid cylinder of mass 20 kgs. Now, when the solid cylinder is kept submerged inside a fluid such that half its volume is submerged. Suppose now half of it is outside and half of it is inside. So alright, so very direct JEE mains type of problem. You have to find out the density of the material of the cylinder given this situation. Just work this out quickly. All you have to do here is make the free body diagram of the cylinder and apply Archimedes principle. Buoyant force, weight, and tension, three forces acting on it. For buoyant force, use the statement of Archimedes principle. Buoyant force is equal to weight of liquid displaced. Oh, Malishka, yes, I noted the correction in the last question. 6 plus 4 by 2. So H's value should not be 3, it should be 5. My mistake. So please note a correction here, people. It should be 5 meters. This is 6 plus 4 by 2. Yeah, now coming back to this question. Centimeters or meters, whatever. Now coming back to this question here. In this case, you will see that suppose the cross section of the cylinder is A. Okay, so the cylinder is like this. Cross sectional area A and total height H. Then volume of the cylinder is A into H. So mass of the cylinder should be density into E into H. Okay. So this is equation 1. Now half of it is submerged. Okay, so the water is only up to here. Okay. So the submerged part has a volume of how much? Half the total volume. So volume of submerged part, so V prime, is equal to A into H by 2. So that is V by 2. So buoyant force will be equal to density of water into volume submerged part into G. So now if you see the cylinder's free body diagram, the three forces acting on it are tension, buoyant force, and weight. So tension plus buoyant force has to balance mg. So tension plus density of water into volume of submerged part into G has to be equal to density of the material into total volume into G. So from this you can see that V prime being V by 2. So the tension should be equal to density minus density of water by 2 into volume into G. So now given that mass of the material is, mass of the object is 20 kg. Okay. This is our equation 2, let us. This one here was our equation 1. So that means density into volume is equal to M is equal to 20 kg. This is what we are getting from equation 1. Okay. And also given that tension when it was 50% submerged is 160 newtons. So 160 is equal to density minus density of water by 2 into V into G. This is our second equation. Now if you compare this equation, okay, that M, which is 20 kg, is equal to density of the material into V. Okay. So if you just divide equation 1 and equation 2, this equation 2 numerically, this equation 1. So if you just divide these two numerically, you can see that you will get heat is equal to 1 minus density of water by density into 2. So density of water divided by twice of that thing's density. So G is equal to 0.8. State G as 10. So this becomes our final answer. So it's all about the free body diagram really. Okay, and using the principle of buoyancy. That buoyancy is equal to density of fluid into where V prime is the volume of the submerged part. Okay, so just note down this part first, then I'll scroll down. Yeah, people, sorry about accidentally I was on mute, so I will just repeat the part that I've just mentioned. So hope you understood the previous question, the calculation fully. So people, hope you've understood this calculation fully. Yes, can you just reply for me in chat? Is this question clear, people? Okay, good. Thanks. Okay. Now moving on to the next part. Accidentally, I think I got muted. Sorry. So for a floating object, the balance of forces occurs in this way. There are only two forces, weight and buoyant force. So weight balances the buoyant force. Okay. So buoyant force is equal to, so any floating object will have only part of its volume submerged. So density of fluid into the volume of the submerged part into G. So this is the general equation of floating. Okay. Now in a special case, if the body floating is what we call an isotropic body. So isotropic means it has a uniform density. Okay. Then its mass can be written as density of the body into volume, where rho is this uniform density and V is the total volume. Okay. So in that case, we get the equation of floating for floating body as density of the material into total volume into G. That becomes density of the fluid into volume of the submerged part into G. So further, this equation becomes density of the body divided by density of the fluid is equal to volume of the submerged part divided by V. But remember, this equation is valid only when the body is of uniform density. So for body of uniform density, rho, floating in a fluid which is of density. So as you know, this can also be called relative density. The relative density of the body with respect to the fluid. That becomes the ratio of volume submerged to total volume. So this is another important special case. Okay. But we should remember that this equation, volume submerged upon total volume, is ratio of densities only when the body floating is of uniform density. If it is of non-uniform density or if it has cavities or something, then it's a different matter. Okay. So let's understand an example based on this now. So next up, what's happening is that we have a solid cubical wooden block of dimension L by L by L, where L is equal to, let us say, 20 centimeters. Now it floats in water. So density 1 gram per cc. So the block floats in water with 60% volume submerged. Okay. So first part is we have to find the density of the wood, which is directly formula based. Okay. Now second part, a heavy metallic object is placed on top of the floating block such that (18 centimeters) is submerged. So now what is happening is, on top of this wooden block, we are placing a metallic body of mass m prime, such that now the portion submerged is 18 centimeters. Is the portion submerged. So we have to find m prime, the mass that we put on top of this, so that the submerged part is now becoming 18 centimeters. Just try this out. So this is a very standard type of problem with application of Archimedes principle applied to applied to a floating object.
Okay, so yes, Manishka is correct, but it will be the weight of the total object. That is the wood plus the water. But has anybody got the answer to the first part? What is the density of the wood? This part. So in the first part, there is only buoyant force and mg, where mg is density of wood, okay, into its total volume into g, whereas the buoyant force is density of water into 60% of the volume, so 0.6 L cube into g. Okay. This is the first part. Buoyant force is equal to mg. So from this you will get density of wood as something. So you work that out. In the second part, what is happening is that you will have m plus m prime g as the new value of buoyant force. Okay. This buoyant force is with 18 centimeters submerged. This was with only 60% submerged. That is 12 centimeters submerged. 60% of 20 centimeters would be 12 centimeters submerged. So that extra 6 centimeters getting submerged because of the extra mass m prime that you're adding on top. So solve these equations and you will get each of the things. Okay, so from the first one, you should be getting the density of wood as 0.6 gram per cc. Okay. So in the first case, mg is equal to buoyant force. So density of wood into L cube into G should be equal to density of water into 0.6 L cube into G. So 60% is submerged. So you'll get density of wood as 0.6 times density of water, or 0.6 gram per cubic centimeter. This is the first part. And the second part, the weight of wood plus the additional weight of mass of metal that you're adding, that is being balanced with the new value of buoyant force. Where the new value of buoyant force is density of water into new value of submerged volume into G. Now that new value of submerged volume is 18 centimeters submerged. So it is 18 centimeter into 20 centimeter into 20 centimeters. Whereas the total volume of wood is 20 centimeters into 20 centimeters. So you can see that the new value of volume submerged is 0.9 times the total volume. So this equation now becomes like this, that m plus m prime g is equal to density of water this, we substitute this here. Let's keep this in CGS unit only, it will be easy. So this is 8 into 10 raised power 3 centimeter cube. Okay, this is the volume of wood, and density of wood was 0.6 gram per centimeter. Okay, so we substitute all that over here. So m prime will become 1 gram per centimeter cube into 0.9 into this volume, where I just calculated the volume. So just a moment, people. I have to reshare the screen. Some data is lost. Yeah. Should be getting the correct value now. Now V is 20 centimeter whole cube. That is 8 into 10 raised by 3. The volume. Okay. So substitute all that over here. So 0.9 into 8 into 10 raised by 3 in cubic centimeters. This. Just a moment, I'll share the screen again. Just hang on a second, I'm sharing the screen. Yeah, so this is the final calculation you'll get for the mass which is added. Okay, so hope you understood both the parts. Just minimize this for you a little bit so that see the whole calculation. Okay, so people hope this is clear. This question fully is clear. So here basically this equation, the M over here is density of wood into its total volume. So that's what we are carrying on this side. This part is actually M. Okay, so people hope this is fully clear. So this more or less brings us to an end with hydrostatics. Okay, so before we conclude today, I'll just give you a brief understanding of what we'll be doing next time, which will be hydrodynamics. So let's look at the basic equations so that we can solve problems the next time. So hydrodynamics, the two basic equations that you have are equation of continuity which is basically based on the principle that if you have steady flow of liquid happening through this kind of a situation, then the volume rate of flow remains constant. So if this cross-sectional area is A1 and the velocity of flow here is V1, then this cross-sectional area being A2 and the volume being V2, A1 V1 equal to A2 V2, which is equal to basically a uniform volume rate of flow. You can see that area into velocity is, for example, if area is in meter cube and velocity is in meter per second, so meter square, velocity is in meter per second, this is a volume rate in meter cube per second. So basically what equation of continuity tells us is that in steady flow, the volume rate of flow is uniform at all places. If you consider any cross section like this, the amount of volume going out must be equal to the amount of volume of liquid coming in per unit time. So that is the equation of continuity. Okay. And the second equation is the Bernoulli's equation, which comes by applying a sort of work energy theorem to this. that, as you know, tells that if a liquid is in steady flow inside a tube such that its motion is happening in a vertical plane, so the vertical height is also changing as the area of cross section is also changing. So if this is A1, the velocity of flow is V1. Here this is A2 and the velocity of flow is V2. And with respect to some standard reference level, the average height in this region is H1. The average height in this region is H2. Then pressure here plus half rho V1 square plus rho GH1 is equal to pressure here plus half rho V2 square plus rho GH. So this is the statement of Bernoulli's equation, where P plus half rho V square plus rho GH remains uniform, where this is called the pressure head. This is called the kinetic head, and this is called the gravity head. Each has a dimension of energy per unit volume. So it's like a work energy relation only, but expressed in terms of energy per unit volume. So this is the statement of the Bernoulli's equation. So next lecture we are going to look at application questions based on this, including the standard applications like the venturimeter, which is used to measure volume rate of flow. Then the velocity of efflux concept. The concept of reaction force due to efflux. So very simple, 3 or 4 standard type of situations where we look at application of this. So this will be the subject of the first part of next lecture, and then of course we'll come to properties of matter, where I'll start with properties of fluids. So we'll discuss viscosity and surface tension. Okay. So all that coming up in the next lecture, people. Hope you understood this lecture, and that's it from my end for today. Okay. So wish you all the best, and continue working on all this. And please let me know in case of any doubts. You can directly WhatsApp me. For hydrostatics, you can do questions from HCV also, okay, or your booklet. But for your J level, for hydrostatics, more or less HCV is enough. So if you just look at the solved examples and the subjective questions of HCV, all your concepts will be clear. Okay, that's it.